Today's class is the first of two classes on relativity, what we call special relativity. So in today's class, we're going to focus on space and time in relativity, and Thursday's class will focus on momentum and energy in relativity. So that's the big plan. Specifically in today's class, I'm going to talk about what I would call the foundations of relativity, the ideas that relativity is built on. There's two foundations, there's two ideas. There are these two topics here. One is that the laws of the physics, for example, Newton's second law, are the same for everyone and for all observers. So that's one foundation. And then the other foundation is that the speed of light is the same for everyone, for all observers. That's the second foundation. So we'll talk about those two foundations. The way I think of them is one of them seems, it better be true, and the other one seems that can't be true. And so we're going to have to wrap our head around foundations that either seem they've got to be true or they can't be true. Those foundations are going to lead us to two discoveries of two new effects about space and time. One's called time dilation, you've probably heard of it. Another one's called length contraction, you've probably heard of that. These are features of space-time in relativity. These are not features of classical Newtonian space and time. So these are the new features of relativistic space-time. And then we'll end up actually with an example, illustration where we'll get on a spaceship, we're going to go to another star, and we'll explore relativity through that example. So that's basically the plan. So just to mention it, this is a Einstein special edition lecture because this is all due to, that's not fair, but let's say it's all due to Einstein. What's interesting about relativity is it's actually mathematically, the relativity we're going to talk about is not very difficult at all. This relativity that we'll discuss is just based on sort of a little bit of high school algebra. The problem with relativity, the difficulty with relativity is the conceptual understanding of relativity. So as you approach today's class, there won't be any difficult math in today's class. It'll be simple, straightforward math. But there are difficult concepts, ideas, notions in today's class. Okay, so before I get on to those two foundations of relativity, I just got one slide to remind you of a topic I'm sure you met in 211, which is reference frames, what I'll call inertial reference frames. So as an example of reference frames, in the picture on the slide here, you've got a train that's passing through a station. And we can think of that in terms of reference frames. It's sort of a classic example of reference frames. We can think of one reference frame as being the platform. We can think of a second reference frame as being the train. So what I mean by that is you could imagine that attached to the platform is a reference frame or coordinate system with which you can describe the location of any event. So through its x, y, z coordinates, you can describe the time of any event through the time on a clock. So that would be the platform reference frame. You could also imagine that there's another reference frame. It's the train reference frame that you can imagine on the train. There's a coordinate system. Again, with respect to the train's coordinate system, you could describe the position through the x, y, z coordinates of an event, and you could describe the time of the event through the clock on the train. And those are two distinct reference frames. As the train moves through the platform, we naturally tend to think of it being the train reference frame that's moving with respect to a stationary platform. But actually, equally valid is if you're on the train, that your reference frame, stationary reference frame, and the platform reference frame is moving with respect to your train reference frame. So both those reference frames are, one's not more privileged than the other. The station isn't more privileged than the train. They're both perfectly valid, equal reference frames, and they're moving with respect to each other with some speed. The word inertial that we tack on at the front of reference frames, that we tack on here always really at the front of a reference frame, is simply that we're talking about reference frames that are not accelerating, that are moving with constant velocity. So that's all that word inertia is. It's just the code word for that. Okay, so now we can get on with the foundations of relativity. So the building blocks of relativity. As I say, there's two things. One, that the laws of physics are the same for all of us. That seems that that's got to be true. The other one is that the speed of light, of a light ray, is measured the same for all of us, no matter our motion. That seems that that couldn't be true to me. So we've got to introduce the idea that some things are relative and some things are what we call invariant. So relative things, you might have in your reference frame, you would have if it's a relative quantity, you might describe that quantity differently. If it's an invariant quantity in your reference frame, you would describe it the same as my reference frame. So here's an example of a relativity and invariance. So look, Ben and Bill are looking, they found this number on the floor, on the grass, and Ben thinks it's a 6, and Bill thinks it's a 9. So they're observing that number, and they observe different numbers. So that's a relative quantity. They agree, though, that if they add the 6 and 9, they both get 15. So there's a law, a mathematical law of addition that they agree on. And that's an example of what's going to come up as we study relativity. There's going to be some things that are relative, like the 6 and 9. Then there's going to be some things that are invariant, like the 6 plus 9 is 15. I'll give you another example. So, at home, I think I do my fair share of the washing up. On the other hand, my wife thinks I haven't done the washing up for 10 years. So that there's a relative thing. But the washing up does get done somehow. And so that's an invariant thing. It always does get done. So we agree that the washing up gets done. We just have a mild disagreement on the proportions that each of us are doing. Anyway, that's a relative. It's like the 6 and 9, and 6 plus 9 equals 15. Maybe it's not a great example. Okay, let's get to physics relative things. So I've got two slides here of physics relative things. I've got slides of a ball thrown into the air from the bed of a truck. And we're going to look at this from the perspective of somebody riding in the back of the truck. And we're going to look at it from a second perspective of a pedestrian standing by the side of the road. And this is just going to be a kind of practice in spotting what's relative and what's invariant. Because relative and invariance is a key to understanding relativity. Okay, so this is the first of the two pictures. This is where the ball is thrown into the air, and this is from the perspective, from the reference frame of the observer in the back of the truck that threw the ball. So that observer might describe the motion. are saying the ball went vertically upwards and then came vertically downwards. There was no horizontal left-right motion. But it turns out that's a relative statement, that the motion, the position, say, of the ball or the speed of the ball is relative to that observer. On the other hand, that observer might say that, well, I can understand that motion because that ball was experiencing the force of gravity, which caused an acceleration, a downwards acceleration. That understanding, that's invariant. Every observer will agree with that understanding. So there's an illustration, we'll see it when we compare with the next slide, where there's some things that are relative. The specific motion of the ball, its position as a function of time, its velocity as a function of time, that's all relative. The understanding that the law of gravity is at work here, causing an acceleration, that's all absolute, invariant. So the other observer is the pedestrian on the side of the road. And when she watches the ball thrown up into the air and come back down, she says that, well, look, that ball's both going up and down, and it's moving left to right. Its path is a parabola through space. Those statements are relative to her reference frame. So she observes up and down and left-right motion in her reference frame. She observes a parabola rather than just straight up and straight down. So that's all relative. But her explanation of what went on, that ball experienced the force of gravity given by Newton's law of gravity, and that caused an acceleration given by the Newton's second law of motion. That understanding is universal and invariant. So that's an illustration, again, of what's relative, what's invariant. So one consequence of that, one sort of consequence of that is that, this notion that we can tell if something's stationary compared to something moving, right? Like I'm stationary right now, and that truck I can see outside, that truck's moving. That notion is really not a good notion because any observer in any inertial reference frame can say that they're stationary and observe the motion of other objects with respect to that frame. There's no privileged reference frame in which we define motion or being stationary. All reference frames, all inertial reference frames can in those reference frames define what's stationary and what's moving. And we can do that because in all inertial reference frames, the laws of physics are the same. So the point of this picture is here. Here's my dog, and my dog is inside one of these shipping containers, and he wants to know if he's moving or not. Well, he can't tell if he's moving with constant velocity motion or whether he's stationary. There's nothing different about the laws of physics. There's no experiment that he could do to actually distinguish whether he's stationary or he's moving with constant velocity. And there's nothing we can do, right, to distinguish whether we are stationary or whether we are moving with constant velocity. And in fact, that question doesn't really make sense. Anybody in any reference frame could use that reference frame, if it's an inertial reference frame, and measure the motion of others. And others in other reference frames could use their reference frame and measure the motion of others. So there's no privileged reference frame where you can say that something really is stationary and something really is moving. All inertial reference frames have equal privilege. Okay, so that's sort of that the laws of physics, that's the first foundation, that laws of physics are the same for all observers. And relativity is founded on that idea, based on that idea. The second, and that kind of seems like an obvious idea, it better be that way. The second one, if you remember, is that the speed of light is the same for all observers, is constant for all observers. To make it clear just how strange that is, if we all watch a light ray, the same light ray, but some of us watch it from a spacecraft, and some of us in motion, some of us watch it from a plane in motion, some of it watch it from a train or a bus or a bike, or we're just standing on the ground. We're all different observers in all different reference frames in relative motion to one another, but magically somehow we all see that light ray traveling with exactly the same speed, 3 times 10 to the 8 meters per second, as we saw in the last class, measured by the Michelson-Morley experiment. So that's very unusual, because if you think of any other, say, waves, like water waves or sound waves, right? Sound waves travel in the air, and they have a certain speed, velocity with respect to the air, 340 meters per second or whatever it is. And if you move with respect to the air, you'll see the sound waves travel at different speeds. Water waves move through the water. Ocean waves, deep ocean waves will have a certain speed. If you move on your boat or your liner or whatever you got, car tire, if you're moving through the ocean, you'll see those waves move at a different speed. So that seems natural to us, right? That if you move through the medium that the waves are traveling in, then you'll see them move at different speeds. But it seems that light is quite unlike that, because for light, you know, whether we race towards the source of light in our rocket ship or race away from the source of light in our rocket ship, we see the same speed of the light ray. It's always 3 times 10 to the 8 meters per second. Let me say how extreme this problem really is, or this puzzle really is. Supposing I got a really fast spaceship, and I could go 99.99% of the speed of light. So I could head towards the flashlight at 99.99% of the speed of light. And I could head away from the flashlight at 99.99% of the speed of light. Now, if I did that, because I'm going so close to the speed of light, we'd of course think that when I'm going towards the flashlight, I see the light coming at me. It's going to be coming at me twice as fast, because I'm running towards it at almost C. It's coming towards me at C. And so I'm going to see it coming towards me at nearly 2C. And if I run away from it at almost the speed of light, then I'm going to see the light crawling towards me at a really slow speed, because it's traveling towards the right at speed C. I'm traveling towards the right at 99.99% of the speed of light. So I'd see it going really, really slowly here, really, really fast here, and that's just not the case. You still see it. If you head towards the flashlight at 99.99% of the speed of light, or head away from the flashlight at 99.99% of the speed of light, you still see it always travel at the same speed, the speed of light, 3 times 10 to the 8 meters per second. It seems like that's got to be impossible. Well, what Einstein did, or one of the things Einstein did, is to realize that there's a way out of this impossibility. And the way out of this impossibility of the constancy of the speed of light is to think about what are the ingredients in the speed of light. What is the ingredient in speed? Speed is distance over time. And so to arrange that all those observers could see the same speed of light, all of us could see the same speed of light, whether we're in the rocket or the plane or the train or the bike or standing here. The way to arrange that is to change our notions of space and time, the space-time fabric. We've been used to thinking about space and time as a kind of stage, as a background, and all the action just happens on that stage and background. But it's a little livelier than that. Space and time are actually connected, joined to one another, and space and time aren't as simple as classical space and time, Newtonian space and time. So we're going to fiddle with change and notions of space and time. Okay, so the next slides are about how we're going to change our notions of space and time. I think the next one is really a little more detail on this problem of different observers measuring light traveling at the same speed. And then we're going to see the consequences of arranging for that by changing our notions of space and time. Okay. So here is just to clarify this problem a bit. So this is an expanded slide of the earlier slide with me traveling towards the light and measuring 3 times 10 to the 8 meters per second. Me traveling away from the speed of the light source, also measuring 3 times 10 to the 8 meters per second. How can we arrange for this? Well, let's start thinking about our reference frames. So this rocket ship here on the left has a reference frame, is a reference frame from which we can make measurements of the light. This rocket ship here on the right is also a reference frame from which we can make measurements of our light. And so I'm going to introduce these two reference frames. The one on the left that's heading towards the flashlight, I called that the unprimed reference frame. I'm drawing here that unprimed reference frame. Typically, we'll just draw one of the 3 spatial coordinates. So that's x here. And then we draw the time coordinates. So this is our reference frame. And then over here on the right-hand side, I'm going to call this the prime reference frame. It's on the spacecraft that's traveling towards the right here, away from the flashlight. And again, I'm drawing here the space and time coordinates. I'm just drawing one space coordinate. I'm going to call it x prime. And then here's the time coordinate. I'm going to call it t prime. So as we think about this problem a little more, firstly, let's realize that this observer in this rocket has a reference frame from which they're going to measure the light. This observer on the right here, in this reference frame, in this rocket, has a reference frame from which they measure the light. And so specifically, what they do to measure the speed of the light ray is to kind of time the light ray between 2 locations. So figure out the distance the light ray has traveled. Figure out the time that the light ray took to travel that distance. And then if you divide the distance by the time, that will give you the speed of the light ray. So that's the calculation that each of them is doing to assert the speed of the light ray. So specifically, what I'm imagining here is the light ray, to help us maybe, is the light ray passing one flag here on the left, and then a second flag here on the right. And the moment it passes the first flag on the left, we're going to call that event number 1. So each of the observers will record the position of that event number 1, and each of the observers will record the time of that event number 1. So they do that. They write it out in their notebook and or their lab book. Then there's a second flag here. So this is going to be the second event, when the light ray reaches the second flag. So when it reaches the second flag, again, the 2 observers in the 2 rockets, the primed, unprimed reference frames, they're going to record the time, and they're going to record the location of this second event. And so they do that, and so they've written out, after the light rays pass the 2 flags, they got in their notebook the space coordinates of the space-time event passing the first flag, coordinates of the space-time event passing the second flag. So they've written that down, and now they're going to go on and calculate the speed of the light ray. So in the unprimed reference frame, that calculation is basically, well, delta x is the different locations of these two events. So that's the kind of the distance traveled. Delta t is the different times of these two events. So that's the elapsed time. And if I take the distance traveled divided by elapsed time, I'm going to get the speed of light. The primed observer will do the same calculation, right? This is the same laws of physics. So speed is related to distance and time in the same way. They're using the same laws of physics. He or she's going to do her calculation where they calculate the, in their coordinate system, the distance between the two events, the elapsed time between the two events. That's the delta x prime and the delta t prime. And they're going to divide one by the other because that's the law about how to calculate the speed. And they're going to calculate their speed. And we know we've got to get the same result here. They've both got to get exactly the same speed. So classically, that's a real problem because classically, in classical space-time, the two time intervals would be the same between the two events. But the two distance intervals would be different because one spacecraft between passing the two flags has moved to the left, the other one's moved to the right. The reference frames have moved to the left and moved to the right. So they actually would measure different displacements between the two events when the light passes the two flags, but they would measure the same times, and so one would get a faster speed, one would get a slower speed. The way to fix it up is actually to give up on that concept that they would agree on the times or the time intervals between the two events. In relativity, in relativistic space-time, that time interval between these two events is actually not the same. So that's a really weird idea. That's a really weird concept. We all think we agree on the length of this class, for example. It's too long. It's too long. But you know, we all agree on 1 hour, 15 minutes. But if we were traveling really fast, we would actually see a different length of the class. And so we've got to give up on this kind of universal, that every observer agrees on the time interval between two events, on the length of time, the elapsed time between two events in relativistic space-time. And that's how we're going to fix things up so we get the same speed of light. Okay, so when you do that, when you give up on that absoluteness of time intervals and make time intervals relative, just like space intervals are relative to the different observers, that's relativity. That's what relativity is. And there's some big consequences of that. So in the next few slides, I'm going to go through two of the key consequences. They're not the only consequences, the ones we're going to talk about in today's class. One is the effect of time dilation, which I'm sure you've heard of. The other one is the effect of length contraction. You've probably heard of that too. And we'll just explain those effects, and I'm going to give you equations, simple equations that describe these effects. So the first one is time dilation. So I'm going to show you two slides about a train moving through a station. And so this is the first one, and this is from a particular perspective, and then there'll be a second one from an alternative perspective. So let me just walk you through what I've got on this slide. I've got two reference frames. That's the first thing that's on this slide. There's a reference frame that's attached to the platform, and it's pictured here in green. And here's an observer on the platform in green. And then there's a second reference frame that's in orange here. It's on the train. And so here's the reference frame in orange. And here's an observer on the train in orange. And I've called the reference frame on the platform, I called that the unprimed reference frame. I called the reference frame in the train, I called that the prime reference frame. Again, when I draw these reference frames, I'm just drawing horizontally one spatial coordinate. There's really three, of course. And I'm just drawing as the vertical axis the time coordinate. Upstairs here, this big blue V, this is the speed or the velocity. the train in this picture is moving from left to right at speed v through the platform. So this is a picture from the perspective of the observer on the platform. The observer on the platform is at rest in this. The platform is at rest in this. The observer on the train, and the train is moving in this slide with velocity v. Okay, so what's time dilation? So on the platform, there's the station clock. That's pictured here. And on the train, there's a train clock, and that's pictured here. The observer on the platform who's at rest with respect to the platform clock sees the platform clock tick at the proper or the correct rate. That's because this observer and this clock are in the same reference frame. So the clock is stationary with respect to this observer's reference frame. In that case, you see the clock tick at the proper rate. So that's what we're going to call the proper time. The time interval between successive ticks is the proper time interval between successive ticks. When that observer in green looks at the moving clock, when he looks at the moving clock, he sees that that clock runs slower. He sees that that clock, there's a greater time between ticks. We call that a dilated time interval between the ticks of this moving clock. And that's because he's observing a moving clock. So this is kind of where we're dispensing with the notion that time is measured by these clocks in these different reference frames is a universal thing. They're always going to agree on this. Because this observer in relativity is seeing the proper time in his clock that's at rest with respect to him, but he's seeing, when he looks at this clock on the moving train, he's seeing that run slowly. He's seeing a dilated, a lengthened stretch time between successive ticks of this clock. This little equation here describes that time dilation effect. So in this equation here, this t prime is, say, the time interval between two ticks that our observer on the platform sees for the clock on the train. This green t over here on the green t on the far right, didn't think about that. The green t on the far right is the proper time between ticks on the clock on the platform. So the t prime is measured by the observer on the platform. The t is measured by the observer on the platform. But this is the length of a tick in the observer's clock, the platform clock. This is the length of the tick in the train clock. You see they're different. They're different by this factor here. You've got to take the time of the proper time and divide it by this factor here to get the dilated time. This factor here that you're dividing by is a square root, or 1 minus v squared over c squared. So v is this motion, and c is the speed of light. And 1 minus v squared over c squared will be, to some extent, smaller than 1, unless there's no motion. And so if this number in the denominator is smaller than 1, that makes the time interval t prime longer than this time t. So that's the time dilation. This is the stretching of the time by this factor here. This factor, where we got basically we're multiplying by 1 over the square root, or 1 minus v squared over c squared. This is a factor that comes up in relativity time and time again. We don't want to keep writing it down, and so it's called the Lorentz factor. And so this gamma here is just 1 over the square root of 1 minus v squared over c squared. So the Lorentz factor is just a function of the motion, the velocity of one frame with respect to the other frame. And it's a number associated with that. If the two frames are not moving with respect to one another, supposing the train is stopped in the station, then v is 0, and then the Lorentz factor is 1. If the train is going through the station, but not very fast, at everyday speeds, then, well, v squared over c squared is going to be tiny, 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 unimaginably small. So really, effectively, the Lorentz factor for everyday speeds is still 1. So you still measure the same time on the train clock that you do on your station clock. But if your train was traveling at speeds approaching the speed of light, of order the speed of light, then this factor is not approximately 0. And this quantity in the denominator here is significantly smaller than 1. And so you get time dilation. You get time dilation, observable time dilations at speeds of order the speed of light. Okay. So that's time dilation. That's me explaining it and then giving you a formula for it. But I want to show there's nothing privileged about this person on the platform versus this person on the train. Because the person on the train can make the same argument. The person on the train can look at the train clock. So the train clock is at rest with respect to the reference frame of the train and the person on the train. And so in relativity, the person on the train measures the proper time in the train clock. The clock's at rest. And so 1 second is a proper 1 second there. When that person looks at the station clock, well, the station clock is moving. It's moving in the opposite direction than the train was moving in the last slide. It's moving at the same speed that the train was moving in the last slide. And so just like we can say, well, look, the train was moving with respect to the platform, we can also say the platform is moving with respect to the train. There's no privilege for the platform. The train and the platform have equal privilege as reference frames. And so it's equally fine to say that the platform is moving with respect to the train as it was that the train is moving with respect to the platform. So here's the train's motion, this big blue V again. And this observer, this is the platform's motion. Sorry, I think I said that wrong. This observer in the train looking at the platform and the platform clock sees a moving clock and measures a clock that runs slow, sees a clock that runs slow, the moving clock, sees a stretched out time between seconds of this clock or minutes of this clock, sees a dilated time. So this is the formula that describes that dilated time again. On the far left over here, this is the dilated time again on this side. But it's the dilated time seen by the observer on the train when looking at the platform clock. This T prime over here, this is the proper time. It's the proper time seen by the observer on the train looking at the train clock. The time dilated time between, say, 2 ticks is going to be longer than the proper time between 2 ticks by this factor, the Lorentz factor, by this factor of 1 divided by the square root of 1 minus v squared over c squared. Again, note that if v was 0, if the train was stopped in the station, then these times are the same. If v is everyday speeds, these times are essentially the same. But if you get the order, the speed of light, if you approach the speed of light, then this dilation becomes a noticeable and important effect. The clock will run slowly. So it's kind of interesting that, both the, let me say this first. Both the, what am I talking about? Who knows? Both the observer on the platform says that, that observer says the train clock's running slow compared to the station clock. But the observer on the train also says, well, look, the station clock is running slow compared to my clock, the train clock. So they're both saying the same things that seem contradictory, that they seem sort of paradoxical But that's the nature of the relativity of time in special relativity. That they can both claim that the other's moving clock is running slow, while their own clock is measuring proper time. And both those statements are true for both of the observers, the train and the platform observers. Just to go through a couple more slides here. This is a graph that shows you the time dilation effect. So look, in this notation on this graph, the dilated time I'm going to call t, and the proper time I'm going to call t naught. So that's a typical language, a typical notation. And so t divided by t naught, dilated time divided by proper time, is the amount of stretching of time. I'm plotting vertically the amount of stretching of time versus the speed of the train through the platform, or the platform versus the train. The speed in units of speed of light. So over here is everyday speed, essentially 0. Over here is something traveling almost at the speed of light. You see that the dilated time and the proper time are essentially the same at low speeds. But as you get up to, I don't know, somewhere around a speed that's 40% of the speed of light, they're 10% different. There's a 10% dilation. If you get up to like 85% of the speed of light, if the train was traveling at 80% of the speed of light, the person on the platform would say the train clock is traveling at, is running at half speed. And the person on the train would say that the platform clock is running at half speed. If we went up to, I don't know, it's 99% of the speed of light, then if the train was traveling at 99% of the speed of light, or the platform's traveling at 99% of the speed of light with respect to the train, then the person on the platform says the train clock's running 10 times slower. And the person on the train says the station clock is running 10 times slower. So it becomes a huge effect at speeds approaching the speed of light. I got a little video to try and show this. This video involves what's called a light clock. So a light clock is built out of two mirrors that reflect a beam of light backwards and forwards. And one tick of the light clock is the time it takes the light to travel from the left to the right and bounce back from the right to the left. That's a tick. So this slide shows you, and I'd encourage you to look at it after the class too, if you've got a moment, because it really shows you why this has to be, why this time dilation has to be if light travels at the same speed for all observers. So if this clock's stationary, that light going backwards and forwards is traveling at the speed of light. If the clock's, say, moving upwards, that light going backwards and forwards is still traveling at the speed of light. Now, when it's stationary, that light has the least distance to go left and right. When the clock moves upwards, it's got to go both left and right and up a little bit. So it's got further to go. So if it's still traveling at the same speed, it's going to take longer. And that's time dilation. So you literally see it with the light clock. So I'll show you that. I watch this to get to sleep at night sometimes. Oh, but that's not actually the video, is it? Duh. Where did I put the video? So here's the light bouncing backwards and forwards. That's traveling at the speed of light. And that would be the proper time. The one tick here is the proper time of the light clock. Now it's moving. Now you see it's got to travel further to get backwards and forwards. It's traveling at the same speed, and so the time interval for a tick there was slower. I'll play it one more time, or is it going to come back down? Maybe. I guess it's just hanging out there. again, the light ray always moves at the speed of light. But when the clock's stationary, it doesn't have as far to go. When the clock's moving, it has further to go. So the tick is shortest, the proper tick, when the clock's stationary, and it's longer now when the clock's in motion. So we see that moving clock tick slower. Gosh, I don't know where I am at all, for some reason. Okay, I want to talk about length contraction. That's the second effect for today's class. I got cut and paste. Cut and pasting is always actually bad. I always make mistakes with it. But I've cut and pasted the two time dilation platform and train slides, and I've turned them into a length contraction platform and train slides. So there's going to be this guy here, this slide, and next is a partner to this slide. And in both slides, we're going to see the train upstairs here. We're going to see the platform downstairs here. Just as a reminder, right, the platform is a reference frame. Here is the platform reference frame. It's in green. It's unprimed. I've drawn the time and one space coordinate. And here's a platform observer in green also. Here's the train, and here's the train reference frame. It's the primed reference frame when I label times and positions. Again, I'm just drawing one space coordinate, and then the vertical axis is the time coordinate. And here in orange is the train observer. And then in this particular slide, I've taken the perspective of the platform observer, and I've said the train is moving, the platform is at rest. That's just a choice of perspective. Both would be perfectly valid. I got rid of the station clock and the train clock, and I replaced them with every station, every train has a meter stick. So this is the platform meter stick, and this is the train meter stick. What's length contraction? What length contraction is that when we measure the length of an object that's at rest, say the length of the meter stick being at rest, then we measure the proper length. So if I take the perspective of the platform observer in green, and I measure the length of the meter stick in that platform reference frame, that's the proper length, 1 meter. On the other hand, when you measure the length of a moving object, like a moving meter stick, like now our platform observer is going to measure the length of the meter stick in the train, that platform observer measures a shortened, a contracted length, a shorter length for the meter stick. So it'd be less than 1 meter. The equation that describes this effect of length contraction in relativity is this equation downstairs here at the bottom. Kind of, you can see it sort of resembles the time dilation effect. Over here, no, let's start over here. Over here, this is this L prime. This is the length of the meter stick that's measured in the train, that's measured by the observer on the platform. So this is the length of the moving meter stick in the train. The L in green, that's the length of the meter stick that was stationary on the platform. So that's the observer measuring the length of the meter stick that's at rest with respect to him or her. And so this equation is telling you that, contrary to every bit of common sense that we've all got, they're not the same. The moving meter stick will be measured to have a shorter length than the stationary meter stick. And the amount by which it's shorter is again determined by the relative motion. So you see here the the proper length, L, in green, is multiplied by this factor, the square root of 1 minus v squared over c squared. And again, this v, this blue v, is the motion of the train with respect to the platform. So this v squared over c squared, it's some number. It might be very small, or if we're traveling really fast, it might be close to 1. That means that 1 minus this number is smaller to some extent, or a greater extent, than 1. And so that the length of the moving meter stick is measured to be smaller than the proper length of the meter stick that's at rest. That factor, again, crops up time and time again. This factor here that we're multiplying by is nothing other than the inverse of the Lorentz factor. And remember, the Lorentz factor is 1 if you're stationary, or if the motion is everyday speeds. It's essentially 1. So at everyday speeds, we don't see these lengths being any different. But if you're traveling fast compared to the speed of light, traveling, of order the speed of light, then the Lorentz factor becomes bigger than 1. So the length of the meter stick, because we're dividing by the length, the Lorentz factor is going to be smaller than the proper length. So that's length contraction. I want to show you it from the perspective of the observer on the train, kind of like I did with time dilation. So now we're going to take, on this slide, we're just taking the perspective of the train observer. So the train observer is at rest on this slide, and that train observer, this perfectly privileged way of thinking about things, train observer is seeing that the platform, and the platform observer is moving towards the left, in this case, with some speed v. And here's that big blue v indicating the motion of the platform in this particular perspective. The train observer sees his or her meter stick to have the proper length. The meter stick that's at rest with respect to your reference frame will have the proper length. You measure proper lengths of objects or proper distances if the object is at rest in your reference frame. That will be the proper length. The train observer, on the other hand, sees the length of the meter stick on the moving platform, the meter stick that's moving past the train observer, as to be contracted. And that's length contraction again. And again, it's the same formula that describes the length contraction for the train observer looking at the platform meter stick as it was for the platform observer looking at the train meter stick. L prime here, now that's the proper length. So that would be the length of the primed meter stick in the prime reference frame. It's multiplied by this factor that depends on the motion of the platform with respect to the train. Here's the V. This factor is smaller than 1, and so you get a contracted length. This L here in green, this is the contracted length of the platform meter stick as observed from the train observer. So again, there's this kind of paradox or puzzle or mystery, whatever it is here, that the platform observer sees their meter stick to be the proper length and the train's meter stick to be contracted. Whereas the observer in the train observer sees their meter stick, the train meter stick, to be the proper length, and the platform meter stick to be shorter. So they both see the same effects for the other's meter sticks. They both see the same effects for their meter sticks being the proper length, the other person's meter sticks being the contracted length. So that there's no one frame that's special privilege or anything like that. They're equally valid. But it just seems at odds, a paradox or a puzzle with our everyday notions of time, because we're locked into this idea that time ticks the same amount for every observer in every reference frame. We don't experience this effect in our everyday lives, so it's locked into our common sense. But time is relative. Just like, when we threw the ball in the air, the position, the velocity was relative for the person on the truck versus the person on the street. Okay, this is just to show you the effect again. it's a similar graph to what I showed you before. So on this graph, I'm using a standard notation where L naught is the proper length, so of an object measured in the frame where the object is stationary, and then L is the contracted length. Vertically, I'm plotting the contracted length divided by the proper length. So this is just a number, and that's this vertical axis here. And horizontally, I'm plotting the relative motion, say, of the train with respect to the platform, or the platform with respect to the train. Over here is everyday velocities close to zero, and up over here on the right, this is speed of light. So at everyday velocities, right, when we're very far from, motion's very far from the speed of light, then the two lengths are the same, essentially the same. L over L naught, the contracted length divided by the proper length is 1. If we went to, I don't know, 40% of the speed of light, so it's a 40% of the speed of light train moving through the platform, or 40% of the speed of light platform moving past the train, then you probably get a 10% effect. That the length contraction is the scale of 10% here. It's about 0.9 rather than 1, this ratio. If we went to speeds that are like 99% of the speed of light, that would be way over here. Then the contraction gets enormous. Look, here at 99 or 98% of the speed of light, the length contraction effect is a factor of 10. The meter stick is 10 times shorter for the moving meter stick than the stationary moving stick. So it's a huge effect. It's a massive effect, speeds approaching the speed of light. If we weren't human beings, but we were subatomic particles travel in this world of high speeds. They would know this as common sense. Of course, things contract in length. Of course, things dilate in time. But because we just live in this everyday world where we don't go faster than, 1, 10, or 100 meters per second, we never get to experience it. We never get to see the effects of time dilation, the effects of length contraction. Okay. Well, that's the end of the foundations of relativity. Laws of physics, same in all reference frames. Speed of light, same in all reference frames. And two primary consequences of relativity. Relativity of time, relativity of space, specifically time dilation for moving clocks, specifically length contraction for moving meter sticks, for example. I want to end up with an illustration or example. So we're going to solve this problem here. This problem is an example that involves both time dilation and length contraction. And so we're going to work through this. In this problem, we're told that an astronaut travels 4.2 light years. That's a distance. 4.2 light years from Earth to a nearby star, Alpha Centauri. And we're told that the astronaut has a spaceship that travels at 95% of the speed of light. So V equals 0.95 c. From that information, we're going to figure out the time measured by the astronaut in her rocket to get to Alpha Centauri from Earth. We're also going to my wife's an astronaut. I'm left at home and looking after the dogs. And we're going to measure the time as me, the spouse, thinks her trip lasts to Alpha Centauri. So we're going to measure these two times, and we're aware now, right? They might not be the same because time's relative to your frame of reference. We're also going to, measure the distances that the astronaut would measure in her rocket to go to Alpha Centauri, and that me, left at home, as usual, would measure for my wife to go to Alpha Centauri. And so we're going to measure those two distances. And again, we know now relativity of lengths or distances that these might not be the same also. Okay. Firstly, I just got a little, I mentioned, I like to do this thing where I'll sketch out the problem, of course, but then I do a couple little warm-up exercises as if I was really exercising. So the warm-up exercises here, I know I'm going to want the Lorentz factor. And I'm also going to want to know what a light year is in meters to get an idea of some distances, to compare some distances. So I did two things here on this slide just to prepare myself. 1 light year is a distance. So that's the first thing. A year is a time. Light speed is a speed in meters per second, say. And so this is a meters per second multiplied by a second or a time. This is length divided by time, multiplied by time. So this is a distance. And we can calculate what this distance is in meters by multiplying the speed of light, 3 times 10 to the 8 meters per second, by the number of seconds in a year. So it's an enormous number of meters, but I will refer to this. More importantly, perhaps, we're going to need a Lorentz factor. So I'm going to discuss this on the next slide, but we've got 2 reference frames here. We've got the astronaut's reference frame, we've got the spouse's reference frame. Those 2 reference frames are in relative motion, just like the train and the platform, or the platform and the train. So they're in motion with respect to one another. We're told the motion with respect to one another. It's 95% of the speed of light. So spouse, me, says my wife's moving off at 95% of the speed of light away from me. She says that I'm moving off at 95% of the speed of light away from her. So we're both traveling with respect to each other at 95% of the speed of light. So I did first, therefore, calculate the corresponding Lorentz factor. So remember that the Lorentz factor is 1 over the square root of 1 minus v squared over c squared. V squared over c squared will be 0.95 squared, because v is 0.95c, comes out to be 3.2. So this is a world at these speeds where relativity is going to be important. If the Lorentz factor was 1, or nearly 1, then, that's our everyday experience. Relativity isn't so important. If the Lorentz factor is significantly bigger than 1, 3.2 is significantly bigger than 1, then relativity is going to be important. We're going to see big effects, length contraction, big effects, time dilation. Okay. So I've got a few comments that I wanted to make. I'm going to introduce them one by one. Because, I'm getting scared because I might run out of time. Worried because I might run out of time. And I want to stop myself saying that because it's wasting time. But I can't. First point. As I say, that both observers are moving with respect to each other. One's not more privileged than the other one. They define 2 reference frames. There's an astronaut reference frame and there's a spouse reference frame, or like the rocket ship reference frame and the Earth reference frame. And gamma, the Lorentz factor, is determined by the relative velocity of those two reference frames. So that's an important thing, is we got 2 reference frames in relative motion. Next important thing. So we're both going to measure the time for the trip. The astronaut measures the time for the trip, and I'm going to measure the time for the trip. Who measures the proper time? The astronaut measures the proper time. For the astronaut, and with the astronaut clock inside the astronaut rocket, the event of leaving Earth and the event of arriving at Alpha Centauri occur at the same location, say the center of the rocket ship. So from that perspective, the astronaut didn't move. It was the stars and the planets that moved in the opposite direction. And so it's the astronaut that's going to measure the proper time, because she's measuring the time in a clock that's stationary with respect to that moment that was leaving Earth, that moment that was arriving at Alpha Centauri. So this is a really important point. From the perspective of the astronaut, she wasn't, and her reference frame, she wasn't moving. It was Alpha Centauri and Earth that slid over towards to the left. And so she's just standing there looking at a stationary clock, measuring a time interval between leaving and arriving, and that's the proper time. The spouse is going to measure the dilated time. The spouse will measure the dilated time. What about the distances? Well, here it's reversed. So this is an important point too, that the spouse measures the proper distance. So with respect to the spouse reference frame, the Earth reference frame, the Earth and Alpha Centauri are not moving. That's not really true exactly. You know, Alpha Centauri is obviously moving with respect to Earth, but nothing like speeds of light. So in the way to think about this is that Earth and Alpha Centauri are at rest in the spouse reference frame. So imagine a giant meter stick between the Earth and Alpha Centauri. The spouse will measure the correct distance between Alpha Centauri and Earth, because those two locations, those two ends of the meter stick, are fixed, that rest in the Earth or the spouse's reference frame. On the other hand, the astronaut is seeing Alpha Centauri and Earth slide by. So that's like a moving meter stick sliding by. The astronaut will measure the contracted length. Okay. Oh, maybe there was one more comment. Okay, the last comment I wanted to stress is that despite their different reference frames, they do agree on laws of physics, the astronaut and the spouse. So if it comes up that they want to calculate the speed from the distance traveled and the time taken, they can use that V equals distance over time. They both agree on that. The laws of physics are valid for both of them. What their distances and times are will be different because of relativity, the relativity of space and time. But the law of physics relating velocity, distance, and time, well, they'll agree on that. Okay, let me write this out. On the device I don't know the name of. Okay, so I made a little picture. Here's the trip. Here's departing Earth. Here's arriving at Alpha Centauri. These are like two events. So this is event number 1 over here. We say goodbye. And then this is arriving at Alpha Centauri. So those two events, and between those two events, like the light rays passing a flagpoles, you know, there's an elapsed time and there's a distance traveled, and there will be different elapsed times, distance traveled, measured in different reference frames. So I've added to my picture all the things I know. Upstairs here, written in this unreadable writing, is the speed of one reference frame with respect to the other. So it's 0.95 c is what I tried to write. And then below it is the corresponding gamma factor, Lorentz factor, that depends on the speed. We said that was 3.2. I've also added to the picture the one other piece of information that we were told in the problem. We were told that the distance from Earth to Alpha Centauri is is 4.2 light years. And if you remember, I explained that the earthling, the spouse, me, will see the proper distance because Earth and Alpha Centauri rest with respect to me. On the other hand, the astronaut sees the proper time. She will see the proper time. So this is the proper distance. So I indicated that by L naught. Let's calculate then. The question asked, I don't know if I ever said what the question was asking, actually. But the question asked, what is the time taken as recorded by the spouse and recorded by the astronaut? So we're going to calculate those two things here. I'm going to calculate so this is T and T naught. T is the dilated time. T naught is the proper time. Remember, the spouse, we said, sees the dilated time, and the astronaut sees the proper time, because the astronaut has the arrival and departure at the same location, whereas the spouse sees the arrival and departure at very different locations. I'm going to work in the in the reference frame of the spouse to calculate the dilated time from the proper length, which is something I know. Let me write down here. What the equation I'm using is a law of physics that is invariant in all reference frames. Is that the speed is the distance divided by the lapse time. In this case, the distance is the proper distance. That's the proper distance the spouse measures. In this case, the time is the dilated time. And I'm just going to rearrange that equation for an equation for t. So I can never do this when I stand up here. Somehow algebra becomes part of the subconscious. L naught over V. Both these numbers we know, don't we? We know 4.2 light years, and we know 0.95 c. And the reason I wrote light years as c, speed of light, times a year, not just because it is, but writing it that way, you can see how to solve this easily. You cancel out the c's in the numerator and the denominators, canceling out units, basically. And we're left with 0.2 over 0.95. That's 4.53. Of course, I worked it out ahead of time. And the units are years. So I see my spouse taking just over 4.5 years to get to Alpha Centauri, travel that distance of 4.2 light years. Let me calculate the other time. So we want T naught. That's the proper time that the astronaut measures. I'm going to get that from that equation that we've already written down for time dilation. T naught's the proper time. T is the dilated time. And gamma is the Lorentz factor. I don't know the proper time. That's the time measured by the astronaut. But I do know the dilated time that I measured. So that's T. And all I got to do is divide by gamma to get the true time, the proper time. And that's 4.53 years divided by the gamma factor. This is really running out, yeah, which is 3.2. This comes out to be 1.38 years. And so that's the time that the astronaut measures. So that's an example, right, of relativity. Relativity of time intervals. Just like the washing up, right? We're disagreeing. I'm disagreeing with my wife now on how long her trip took. I said, you went away for 4.5 years. And she said, it's only 1 point whatever years, only 1.38 years.